they're talking about this, and I see all this stuff that's all steroids coming out of California, so they come over here and they're like, what?
So you know we're doing the H2S stuff with Unisearch in California.
Yeah, we monitor everything, you know, so, we know what's going on, but this is cutting edge stuff. What we're really more concerned about is, technology will take care of it, but it's the regulations that sort through how, you know, Republicans are in it going one way, Democrats are in it going another way, and then we're in the middle kind of going, okay, what are we supposed to do today?
Yeah, that's kind of where I'm trying to go with.
That's my directive, to see the current state of the regulations.
Okay. Well, I'm not really going to talk much about the state of regulations. More, okay. What do you need to do to come up with some reasonable regulations? And what do you need to get
Something we're gonna stick. So this stuff, I just left a legal presentation. She was telling us to look, well, I used to be with GCQ, there's nothing because I drink Kool-Aid, but yeah, I think they should have a 90% reduction in whiskey right now. And I think unicorns should fly to the sky and drop lollipops. They say these kind of things like, look, I'm not going to save the planet.
Yeah.
I don't like the planet. But there's got to be a way, like when Obama came in and he's like, okay, we're stopping oil. And then everybody's like, you know, ride skate.
Yeah. Let's pull all the methane out of the atmosphere.
Yeah.
Get rid of all the methane. Let's drain the swamps, literally.
Don't give beans to the cows.
Yeah. Oh, we got some feed that might help the cows. What's going on with Tamara?
How about the feed my husband? I was in the Louisiana. I always forever down my mind. I'm sitting there. Yeah, I heard somebody talking about post up. Said, hey, what do you do? So they're talking to me. Hey, he's from a biotech company. And they were talking about what I did. And like he said, I made my pork off fowl and chicken. So you have my attention. That's your chemical. What's that? Okay, good. He's explaining to me, and I didn't know this one. And I'm smart. There are 6 enzymes that chicken needs to survive. They self-produce 4 out of their body. 2 they have to find externally by 3 bugs and bugs and such. This company has recreated that enzyme, not steroided it or changed it or hybrid it. It's the same steroid, and they freely spray it on the brain. They now raise a chicken from an egg to a McNugget in 37 days.
Wow.
And I said, wow. He said, well, that's not the best part. I go, well, that's crazy. He said, their white coats are looking at it and saying, that sure is a lot of waste with the beaks and the legs. He says, so what they're trying to do now, they're trying to raise a chicken breast and feature it.
Yeah.
I said, well, I'm going to stay away from the Chick-fil-A for a while. Isn't that amazing? 37 days. Eureka. I just found out Netflix. I saw the whole series.
Where they talk about like humanely raised chicken.
Really? Because I saw every episode. I loved how Stanley cooked. Really?
So that's some kind of beta blocking causes everybody that eats chicken to go.
That's cool because I watched that series and it stopped. I was kind of sad. It just came on Netflix. I started again, but that's funny. It's a great show. I love hearing that. The sheriff. They had a big robbery. Man, we get to take fingerprints. We get this. He goes up to the bank's missing. It was a great show.
Yes.
So you're Randy.
Yes.
I'm Nick.
Okay.
Situation here. What is it?
Andrea?
Andrea, hi. And this is the test subject serial number 1 for
Yeah.
the COVID.
Yeah, he's the one of the guys. He's one of the early spreaders.
001.
Yeah, I brought it to America.
And where are you guys located?
Houston, Lisa.
Okay. I'm up in Livingston. Because I'm trapped up there. I think my mom 4 years ago. I was going to leave in 4 months and COVID hit. And I'm like, oh, shoot. So I'm trying to get a house. The housing market's at least figured out. So.
Let's California check it out.
But it's great. I had a house price point. It's a nice house in Houston, like 185,000. That same price point. They switched it. This is the same company that when you're looking at on the sheet, it's about one. Switched it. They had that power. You don't have to leave your sheets. That's a 1.5 years. Just switching that.
Go awesome about that.
You don't have to get out of your chair.
Oh, okay.
And you endured that same lawyer that I endured earlier, Stephanie. I'm talking about.
That was great.
It was great, except what she said. Okay, I'm not going to Kool-Aid, but we want to drop 8% of the VOC right now.
Right now.
She wasn't for sure, but she was very blue.
Well, it's the first one after lunch. We'll give it a couple more minutes in case people spill
Thanks.
I told everybody we were waiting on you to get started.
Thank you for waiting. Sorry for being late.
Jeez, I've been waiting here the whole time.
We might go through,
Apologize.
we might go through it once.
Did you have two sandwiches or what?
You've been looking on.
We're up to Q&A now, so if you got any questions, presentation.
Remarks, just
Mark,
remarks.
just remark.
Okay, we can start now. So I'm Randy Gibbons, company's Terra Applied Systems. Title probably changed from the letter, what they handed out. It's not really about California. We wanted to talk about what we learned in California. And from a different perspective, I think that a lot of others can look at it. Our company, Terra Applied Systems, we got into the open path business for industry in 1992. The company that's now Cerex was ETG at the time. They had an open path of TIR. They wanted to commercialize it for industry. And they talked to us and we tried to start doing that. So our focus has always been the industry side. We've done some support for like community groups. We talk to regulators, but our focus is applications industry. And so we have a different perspective from a lot of other people. We did worked on about 8 different locations in some way or another in California with our Fenceline systems. And I was planning to do this, and we've been doing some work with Robert Crampton. For a while through all this stuff, he was working for Argos, who did a couple, 3 or 4 projects in California, and he was one of their technical guys that really knew what he was doing. And we've been trying to do some work with him. I said, okay, between you and me, we've seen a good part of the programs at every single location in California. So let's get together. Let's see, okay, what went right, what went wrong? Let's pick out some of the biggest problems and let's discuss those and try to address them. And so we started doing that. And so a little bit about our experience in California. The first California Fenceline system that went in at refineries was in 1996, and that was our project. So they put in a couple of FTIRs, a couple of UVs, and 4 different laser units. And so we started with that. We were doing remote support in 1996 through the internet of the system from Texas, and then we'd show up when something went wrong. It needed to be addressed. Most recent one, like I said, we worked at 8 of the refineries in some way or another. The other refineries, we were working with the engineering companies that were doing them, and we supported the engineering companies, mostly through a friendly means. So they'd ask us questions, and we'd work with them, try to get things squared away. Rob He was with Argos. They've been working, he's supporting Argos. They've been working California systems. He's been out there for 10 years. He's got his PhD in open path spectroscopy. He's a little bit more of a hardcore spectroscopist than I am. Quite a bit more, actually. I kind of fell out of the spectroscopy, and we've been focusing more on how to put systems in and make them reliable. So that's what I want to talk about. And we looked at what went on out there, the troubles we saw people have, and how the troubles had to be solved, and how perhaps they could have been involved. And we pulled all this together, and I started to group them, and a lot of it fell into design. And for various reasons, the design process or what went into the design was ineffective or problematic. And so that was our focus. That ended up being a big part of what we saw. So we're going to talk about the design process. We'll talk about the experts involved and how sometimes that was problematic. We'll talk about a little bit about the implementation. So look after that, quality, and operations, maintenance. And I don't look at this to say, okay, California messed up. California didn't mess up. I look at this and say, okay, this illustrates how to do and how not to do systems from a full system perspective, from the definition of the regulation to the development of and a selection of the technologies and the systems that go into it, operations and maintenance all the way down the line. So just pulling out the biggest things that we see that you really got to watch out. So from regulation and design perspective, the background, I guess, is there was an incident in Rodeo, California in 1994, I think, or 95, and they had a release from a tower that went on for about 16 days. And they didn't tell anybody. And there were complaints from the neighborhood. And so when their land use permit came up, they were going to be denied use of the property unless they did something pretty drastic. But so they agreed to put in a monitoring system and on the fence line to monitor it. And so we ended up getting that project and we put in that system. So that was kind of one of the big things that really kicked off this Fenceline stuff in California with a lot of the regulators. But then there was, of course, there was a fire in Richmond. Some of the other guys this morning talked about that. That was big and visible, and that pushed it farther. And there was out of that came some recommendations for Fenceline monitoring. And then there's a very strong political environment, strong activists, very vocal and very powerful, of course, in some of those. And so it's not like the industry really wanted to do this, but they were kind of pushed into the kicking and screaming. There were some purposes identified going through that process. One was to address the public concern for emissions minimum from industries. There's a real concern in the public that they're poisonous, and so they want to be able to keep an eye on that. There was in the working group document talk of emergency notification for offsite impact for emergencies. And we also desire to look at the long-term data and see how toxicity may affect the people off-site. These didn't all get put into the systems or to the regulations. The regulations were rather vague. Kind of like what they were talking about Colorado today. There's a regulation out there. We don't really know what the specific requirements are. And that turned into some difficulty trying to implement programs, design and implement programs. The coverage requirements were also vague. They were defined by a plan review process, which was a long process, and you could predict it very well. The detection requirements, again, with detection limits, exactly how you determine detection limits are rather vague. There's a lot of vagaries there. Reliability, they say, well, 95% uptime, or they throw numbers out there that kind of define. So there's a lot of vagueness in the whole regulation process. And the performance assessment was not qualified. The purpose was fairly well demonstrated, I think. They wanted to address the public concern. There were people screaming, people causing trouble, and they said, look, we got to do something. So let's force this. And they did want some notification, turn real time or near real time offsite. So that was the purpose was fairly clear. Let me step back. So I go back to this one. Part of the design process, I have a little bit of a snippet of what might be in a design process. And the first thing is to understand your purpose. And this is true of fence line systems. We don't do fence line systems mostly. We do a lot of systems that are process safety management or safety systems for gas detection. And one of the first things we do on all these systems, and we did it with the fence line systems. Okay, what are you trying to do? What's your purpose in doing this? And when we go in for safety systems or process management safety systems, they know what the purpose is, or we can define it pretty quickly. We went into California. Okay, what are you trying to do with this? So there really wasn't a purpose defined for it. That guides everything else. So the regulations really had no clear purpose. And the project teams, the industry project teams, pretty much unanimously had one goal. That's to comply with minimal risk, including minimal financial risk. They wanted to comply with the letter of the law. They wanted to put it in place. And from a management industry perspective, how do you argue that? They've been told, here's what you do it. And so they comply. They wanted to meet the compliance deadlines. They wanted to minimize the cost to compliance, which is good business. Assess average concentration at the fence line. And fence line measurements are a little bit strange. So we'll kind of talk about that a little bit. Manage and reportable detections. No false positives. False positives are much worse than false negatives. And because they bring real trouble. They must have wanted to isolate it from operations. They wanted to operate, they wanted completely separate systems. And this was uniform through pretty much all of them. And operations were pretty much blind to these things. And they marginalized the emergency response support, which kind of went against one of the working group purposes for doing this. Okay, if there's an emergency, we need to support it, right? We need to know what's going on. And that was mostly marginalized in their response structures. So what should it look like? Okay, if I were designing one of these, what would we want it to do? And what's responsible as an industry citizen? Timely notification of offsite impact. If something happens, you want to know about it. There was a release in Houston not long ago, and I think it was methyl mercaptan, and it stuck like all South Houston, way down toward Galveston. There was no word from industry that there was a release. They knew it. There was a shelter in place a little bit closer. They didn't say anything about it. You really need timely notification. Assess long-term exposure, health and safety. Of course, there's acute toxicity, which is where we normally operate. We work with stuff like anhydrous ammonia, hydrogen fluoride, and things with really acute toxicity. So in our mind, you want to be sure it's right, and you got to take action on it. So that's normal for us, not so much for the environmental or the community monitoring. The long-term toxicity, there's been talk about that. Environmental impacts and uses. A lot of smells and things like that are nuisance smells are not really toxic. They need to be addressed. And then to support public confidence that their industrial neighbors do that they can assess the hazards and let us know if there's a problem. So it's good citizenship and good public relations there. And then there's operator due diligence. If you got things that are going to be a problem, you need to let people know. So we went into it. It's like to do everything else. What's the purpose? And you have to design with a purpose. Define the expectations, define the deliverables, provide realistic timelines to these things. And this is one of the big issues with California and that was mentioned by a couple of the other guys, speakers this morning, is these timelines were really accelerated. The first project we did, we had, I think it was less than 6 months to get it designed, built, in place. So maybe a little bit more than 6 months. So most of the rest of them were about a year. But the definition was going on this whole time. So how do you design to something that has no requirements? Define the deliverables. Data quality was, and with some places still is, an issue. So, but you need to define the purpose. You need to know what you want to do. You need to do it. It's too late for California. They're still deciding what they're going to do with all this stuff. But you know, there's Colorado, there's talk in Texas, Louisiana's floated it, Pennsylvania's floated it. So there's a lot of government organizations trying to push this, and it can be pushed better than what they did in California. California was a good stuff. Design the requirements for the purpose. Don't just say, well, we have to go put it in Fenceline monitoring because it'll make everybody stop the playing, right? You want to know what the hazards are. And they did this to some extent in the Bay Area. There were some proposals based on, okay, well, here's your site hazards, and here's your location hazards, and let's define what the system needs to do to address those hazards within the regulation. And there was some success in doing it there. In the South Coast, it was attempted, but it more or less came back, no, do the whole perimeter for every line. And so that's what they had to do. Whether there was a hazard in that direction or not, that's what they had to do. Design it based on technologies, best technologies. Technologies, the expectations for the open path systems were a little bit high with the regulators. They were, I don't want to say they were oversold, but there was a lot of salesmanship from the vendor side and from the consultant contractor side. And there's been a lot of development with the technology since they were installed. And they're a lot better now than they were then. But it was a little bit of overselling thing. And then realistic timeline to enable due diligence. The projects were difficult because decisions were made fast. They had to be made fast to meet timelines. And trying to vet all of those decisions in the timeline allowed was very difficult, and it resulted in some eventual problems with some of the systems. So from my perspective, my background is chemistry, analytical chemistry, systems, especially measurement systems. And I see people, they say, well, I need to measure this. So what do you need to measure? And so when you design these systems, it's not easy to say, oh, go measure things. It's easy to go out there and set up a machine and collect numbers. Lots of people do that. And it's a little bit harder to make those numbers meaningful. You have to look, you know, what's my source? What are my issues, my measurement issues? So you have to look at it closer. Then if you have a purpose and you have an application, it's even harder to get the experiment designed, especially in a full real-time mode, to make that measurement. And so it takes very careful planning to produce that measurement. And the purpose of the measurement is key to doing that. So a little bit of change in gears here. Like I said, we picked out things that were problems or issues. So I'm going to hop around a little. Talking about sampling. So the open path systems, the regulators said, you're going to do open path or some equivalent technology. So they settled on open path. They had open path Rodeo, they had open path over in Richmond, and people liked it. So let's do open path. But there was some talk this morning about the strengths and weaknesses of open path versus points. And point systems tend to be fast. You have a point and you can say, I have a concentration right here. And so people know what to do with that, right? Say, okay, I know how to act on that concentration. But if you look at my little sketch here, if you have a release, you don't know if the center line of that release, the high concentrations that goes to your point, or it's going to be off the point. And so how do you really assess what's going on? If you have it go past several points, well, you can do some analysis and say, okay, this defines where my foot is, and I know what the concentration is in that area. The problem with path measurements is you don't know what you're measuring. Okay, you can measure your average concentration in the fluid, but you don't really know what the concentration is anymore. And it may be a narrow path, it's going to give you a narrow plume, it's going to give you a smaller number. It could be a broader plume, it's going to give you a higher number. Because the nature of the open path measurement is it's just counting molecules in the path. It doesn't know the concentration at any one point. Path measurements also, they're not really industry standard yet. There's several open path type systems out there. They primarily try to relate to a given concentration. But again, if you have a plume here that's 1 ppm, that's 50 meters long, this is going to read 50 ppm to analyze. If you have a plume that's 50 ppm and 1 meter wide, it's going to read 50 ppm meters to analyze. So your path measurements don't tell you what's going on at any one point in time. And coming up with HSE standards, health, safety, environment standards, and applications to do that is awkward. But path measurement is cost effective for certain applications. It's a good indicator of mass flux. This was mentioned this morning. What's the flux coming off of my site? With the gross flux coming off a large site, you don't really care where it is. I just want to know what am I emitting coming off that site. And path measurements are really good for that. The calculation is fairly straightforward, right? The path average concentration. If you take an average, but assuming that every meter has the same concentration, you take an average, you can get, okay, this is the average concentration across that path. But if your gas is concentrated in one area, this doesn't really tell you. You're diluting it by all the other space. So it really doesn't tell you the hazard that's going on in the path. It can tell you, you have to look at more tools to really assess that. You can estimate the concentration at the intersection. This is what we do with a lot of the safety systems. We say, well, based on your site and distance, your average plume is about 20 meters wide. So let's say that the concentration is probably contained in that 20 meters. And so you can estimate a long path and say, okay, your hazard is probably close to almost 20 meters. So let's take action based on that assumption. That informs us. You can also estimate the source term if you know where it is. The source term is how much is coming out, how fast, what elevation. And you can estimate the area emissions, which is related to the flow. So there's really good things you can do. Again, this all goes into the design. What do you really want to do? We had a system go in, it wasn't in California, but they wanted to use a long path so they could get really good detection limits. Okay, never mind the plume was probably only about 40 meters wide at that point. They wanted the whole path average. They had issues with the long path that kind of showed up in this application. And they show up in California systems too. The longer paths, you have more noise. Okay, so your signal to noise ratio isn't as good. So you really don't pick up as much increased sensitivity as you expect from going longer with the sample. You get spatial pollution because you probably have a plume that's restricted, and again, you're averaging all these zeros outside the plume, so you're essentially diluting your measurement. You have signal loss, which when you have compromised atmospheric conditions, you're going to lose signal faster, right? Because they go offline. And spatial resolution loss. You don't know where it is. There's some things you can do at intersecting paths or overlapping paths and things like that, but it's really hard to get spatial resolution to find out where the source is if you're trying to take action operationally on this information. Shorter paths, you get a higher signal to noise ratio, and we had one installation where you cut the path in half, and our detection limits dropped by 2. It's completely counterintuitive, but the noise just went away. You have better signal stability, so your operations are stable. You have less background problems, especially with the optical systems. You have less ozone interference just from ambient ozone. You have less water interference, so the background becomes less of a problem. And you have better spatial resolution. And we've done this with smaller systems. We put in large perimeters, we put in smaller paths or points. You go out, I mentioned that earlier today, and you define where your source is coming from. And we had this discussion with one of the South Coast refineries. We did a show and tell, and the refinery manager came down. He said, "Oh yeah, this is really nice to know what's going on the fence. Like, well, what's that do to the operational? You know, when there's a problem, I want to know that I've got a problem." And so we discussed these things, you know, section the area, put in shorter paths, put in another protection, type. Fast sampling cycles. Okay, this is something that the regulations in California drove a 5-minute sample cycle. They said you have to update your results every 5 minutes. So most of the systems, initially, and I don't know how many of them are still that way, they said, "Oh, we're going to just collect data, we're going to average it for 5 minutes, and then we'll report it." Or we're going to integrate signal for 5 minutes, and then we'll report it. We found some issues with that in some of our systems. You can't detect short releases. And this, again, design goes to purpose. Is your purpose to say, generally, we have this many molecules going out, or is your purpose to say, we got a problem, now we can do something about it? And by the way, we haven't had a problem, and now we can tell you long-term how it behaves. So when you average things over time, your short releases get averaged out with all these zeros. That's so you lose your sensitivity for short releases. And when we see releases in a lot of our systems, they can be short. You know, they can be 20 seconds to 5 minutes. And by the time you get out to a fence line, that's lost. You get faster notification. You get temporal resolution. You know when it happens. Okay. If you do hourly averages, you know, it's the same with SUMA canisters. You know, you do SUMA canisters for 14 days. You don't know when things happen, right? I don't know what good it is other than I'm in trouble now because I haven't exceeded. If you go faster, you get temporal resolution. You can see where things happen, and you can understand what's happening. And you get better spatial resolution. Correlated with wind direction, the faster your samples come in, the more sample points you have to tell you when the wind moves. My release moves in and out of the path, or between one path and another, goes in and goes away. So you can pretty quickly get down to a point where you can say, this is coming from this general direction. So operationally, it's much more useful. So for faster sampling times, do you sacrifice detection limits? If you're careful, you don't. You can only collect data for so long and average it before you start to lose the benefit of noise averaging out. And so, you know, we have systems out there running 1 second resolution. We have other second, you know, up to 30-second resolution. And the detection limits from operationally from requirements really aren't effective. Significant. And that goes to the short sample time. So how are you going to sample? I mean, you know, what are you going to collect data before you report it? And then long averaging cycles, you temporally shorter releases or releases coming in and out, you delete them. You know, you'll have detections, you'll have detections go away, and they all get deleted. So you get a good, nice long range concentration, but you don't really see sometimes what's going on. So this goes to your application. Are you doing this for safety applications, for notification, let people know what's going on operationally, or not? You know, are you just moving into the fence line so everything's fleshed out and we don't see much? So do you want it to be operational or do you not? One thing that was in the working group document, it did not put into my knowledge any of the California systems, and we've done this a couple of times, is it's good to know what's on the fence line. Okay, we had a project and they wanted to spend, the salesman wanted to have them spend $24 million to cover their fence line with analyzers. which would have been really nice, right? But I go in there and they say, well, do you really want to know what's going on with the fence line? Well, the operations guy said, no, we want it on top of the unit. Okay. Okay. So what they wanted to do was make the measurement, use our dispersion modeling software to project the concentration of the fence. And this was addressed in one of the California working documents to do this. And the company that did that was trying to push it, but they didn't have any success. But you set your paths far enough away from the sources to where your plume is well balanced. You can make good predictions of what your plume is like, and you can make concentration measurements that are closer and higher. Okay, then there are several software packages out there that'll do this, automated ones. They take that information and they project what the fence line concentration is. So you can make your measurements at a higher concentration with higher reliability than project the fence line concentration. So first company we did this at, their project went from 14 or $24 million down to $2 million because we came in with a closer perimeter, projected a fence line. They've had incidences that they had to model, and they checked it, and they're very happy with it. And they've been running for 5 or 6 years. So could be more cost effective. It depends on your application. Depends on what's required in the application. Still around design. Again, I said everything seemed to coalesce around design. Things were problems, or things were expensive because the design wasn't possible. So over time, it's good to set these things up and they work great. And then after a while, they don't work great. Okay, things degrade over time. The longer they're out there, the longer they degrade. The system performance degrades with operating conditions, it degrades with getting dirty. The detection limits start to increase. And so what are your detection limits? And this is an issue, I think, with the South Coast is, okay, how to calculate detection limits? And you have dynamic systems out here making measurements. And you have the atmosphere changing, you have the systems changing, you have the optics changing. And the detection limit on a clear day with no humidity is great. This is what the systems were promised from the manufacturers. Not trying to be deceitful. This is the detection that you can get. But at 3 o'clock in the morning, you've got a metal stable atmosphere. You have some condensation. You have some almost condensation. The light doesn't act the same, and the systems are noisy. And you can't reach the same detection limits. You just can't. Or even worse, it's foggy, and you're just kind of in and out of enough light to make the measurement. So, in the design, the detection limits that are promised and how the detection limits need to be calculated and reported need to be addressed. And it still, to my knowledge, hasn't been addressed well by the regulators. I think it's been addressed by the South Coast, but I'm not sure it's been addressed well. You may have some ideas on that. And the reporting needs to reflect this. So, again, how much time do I get? A little bit. Okay, another issue might be a touchy point to some. Going in, and there was lots of money to be had. And there are lots of people who came in as experts. And some of these experts have done one graduate project doing open path, and so they were an open path expert. And that doesn't work. Battling experts and people who have ideas on how things work, open path systems aren't normal. They don't work that way. And so that's an ongoing problem with us. We've done over 100 projects with full-time open path systems like this. And it's a problem, probably about half of them. They have other experts. Like my graduate project, an open path spectroscopy doesn't make you an expert in permanently installed systems. Getting these things set up, you're running them for a day or 2 or 3 is easy. Getting things set up to run all the time, high reliability, the design, the setup, everything is not that easy. And in engineering, engineers work with a certain engineering paradigm and certain project drives. And certain personality traits that sometimes tend to go with engineering. But just because an engineer is a good industrial engineer or a good mechanical engineer doesn't make him an expert on designing open path systems. And some of the most expensive project problems we've had came from engineers who did. And that goes from this. Most industry project teams are engineering driven with an engineering paradigm, and engineering is the first and last step. We had projects go $2 million over because they didn't want to change their drawings during the first month. The first month, they had drawings so far to get their budget set, and they didn't want to change the drawings. So all these problems were built in, and it took $2 million extra dollars. Applied science and technology systems, which is what we're talking about, right? And require science and technology designs. You can't shortcut the design and go directly to engineering. That's the continuous problem. And it needs to be supported by good engineering. Again, experts, we talked about this a little bit. Vendors are experts, of course. Vendors are experts in our machine, not necessarily the systems. Consultants, one little project, 1 year working somewhere makes you an expert, and people listen to you and make problems. Conflicting experience perspectives. Anyway, get different. We had one project, and there were about 6 different subject matter experts on it. It was a continuous battle to try to work out this. And then engineers, again. Engineers are good. Engineers have a perspective. I like working with good engineers who are open-minded and can listen. So some of them are that. And it kind of goes to this. Open path systems are pretty much always multidisciplinary projects because you're integrating the machine with your environment and trying to make a measurement for an application. So atmospheric sciences are important. Physical sciences, spectroscopy, of course, chemistry, believe it or not. I'm a chemist, so I can't do it. Analytics, what do we do with the data? How do we extract the information we need to make it actionable? Structures are a big deal with open path systems. Little details of the structures to make a great project. Electrical systems, material science, mechanical, all of this has to be tied together. Integrated knowledge and experience is critical. Somebody, they call it a technology guru in some industrial engineering circles. You have one person who knows enough about everything, or one organization who can help keep everything tied together and get a good output. You have one person with too much control who doesn't see that. It can get really expensive really fast. Transition. Design to reality. When you go from design to implementation, often there's a continuity loss. And you go to contractors who haven't seen it. Sometimes you change engineers. Engineering paradigms are maybe different than what needs to be done. You just don't see the structures are a big part of it. In a long path, a little motion in a structure is a big motion 500 meters down the path. And so building the structure so that they're stable for that is not normal engineering. And I think we've had 1 or 2 organizations who actually could sort of calculate motion close enough to determine if our structure is going to work. Most of them will say, oh, we did a wind load analysis and it looks fine. Wind load means nothing. So the engineering paradigms of construction just is different. Industry norms going from site to site, everybody has different standards. Some of them are really tight, some of them are really loose. We had one, they showed up, said, oh, there's your left, go do your thing. Well, you don't do that in most refineries. You have to be certified. You have to understand the industry norms where you go. Trades, the tradesmen, the electricians, the laborers, sometimes that's a problem with people. We're very careful. That's not a problem with us. We get along really well with the trades. We've seen others who didn't. Vendors come in, they know everything, the trades just kind of blow them off. They can make things go badly. You work with the trades and it goes better. Troubleshooting and reworks. So the whole transition thing, things come up and it takes time and it takes money. And it can make the project really bad. And then standards compliance. If you don't have any standards to comply to, there's no compliance. And then it's your fault when it's off. Implementation completion. Okay, this is getting expensive. That's good enough. Just leave it alone. Okay, and that's a real drive. Goes to operations, data, things. I think we're getting close to the end of time. Yeah, operations compression optimized. So you go into operations and okay, we got this. We got to watch the cost, and so let's hire somebody that's just got a bachelor's program and put him up there and do it, or hire somebody with no experience in open path. And that's a problem because they can't troubleshoot when things happen. Okay. All that to say, you can't just go put these things out there and let them run and have it work. It takes, we've been doing this, I've been doing this, it's 25 years since the Rodeo project that we've been doing this. We've done 100 systems. And we walk in, and we do this with a lot of the California projects. We'd walk in, hey, we're thinking about doing this and this and this, and they said to do that. We're like, no, you don't want to do that. And you don't get that experience in just a year or two or three. So you got to be careful who you work with, and designing, program, the regulation. I don't know how many of you have influence working with the regulators, but it can be designed, and the California systems work. They weren't designed to accomplish anything, honestly. This was a frustration for us. They're going to do some good. They weren't really designed to accomplish anything. But the systems we normally design, we go in, we know where the problems are, we know what needs to be designed, we know what needs to be done, and they work. And it's a lot cleaner, it's a lot easier, and it's a lot less expensive. So hopefully, as this matures and this whole Fenceline monitoring movement, as it is, we started in 1992 to do Fenceline monitoring, and now we're doing Fenceline monitoring. That's how it's going. Most of our systems are short. But hopefully, as it matures, we learn things out of California, we learn things out of other places, we get more talk going. Let's be realistic about this. Hopefully, it becomes realistic that it actually becomes more beneficial to everybody. So, yeah, I've got 2 minutes. Yeah.
When you mentioned you said the long path, there's noise, short path, there's better signal to noise. Can you quantify in meters what you meant by long path?
Well, one of them we did, we actually used a folded path, and the full path was 1,200 meters. And the spectroscopy was good there. It was good for that wavelength we were using, but the noise in the system was such that we really couldn't get, we were looking for a 40 ppb detection limit on this gas. When it went direct down to the retroreflector and back, we got down to about a 3 or 4 ppb detection limit, huge stability, just because we made that change. So, and it depends on the gas, depends on the wavelengths, it depends on a lot of things, exactly what a long path is. Like for benzene, a long path is about 500 meters if you're going monostatic, and because you start to see breathing and interferences from ozone and oxygen and things like that, which is in some conditions just aren't stable.
And what's your tolerance for relative humidity? Can you go up to 95%, 100%?
That depends on how far you're pushing things, because you can see things well at higher detection limits. It depends on where you want to cut off. Like we're trying to do we're doing H2S right now at a refinery with a laser. And it's actually working really well. The issue for several months has been when we get into these marginal conditions, then we see funny things and we need a high reliability measurement. And so we're cleaning up those margins to where we can do it, doing some data analytics.
You don't worry about condensation on the mirrors?
Condensation will scatter the light. Oh, on the mirrors, we try to keep the mirrors clear. Yeah, that's what will kill you fastest is the water on the mirrors. Even worse than water in the air. So it hits that surface and it just scatters. So yeah, we have several ways to manage that. by design or by tools.
Okay.
Okay. Well, I think my time is up.
You're looking up the presentations.
I don't know. I think this guy.
Are you loading up the next ones?
Yeah.
Okay.
Are you 145?
Yeah.
Oh, am I in the right room?
Is it 415B?
Is it? Oh, 460.